can we record your talk?
Yeah, that's fine with me.
Okay. And I think we start. Today we have the Professor Pell, Gorkom. Yeah, will speak with us. Yeah, and let's start. I share your screen.
Yeah, here, let me try to pull the right thing. Hold on. All right, are you seeing it full screen?
Yeah.
Okay. Okay, should I get started?
Yeah.
Okay. So I'm just gonna talk through the proposal that we submitted. I guess it was in January, and then got funded. So this is to do technology development to do high contrast imaging into the ultraviolet, or the alternate title is Scoob UV edition. Um, so, oh, before I dive into it, I was just going to go through a little bit of the background. It's going to be kind of light on the science. So, um, but the basic idea is um, the motivation for wanting to do high contrast imaging at the UV is really to detect ozone. Um, and so this figure on the right, I think probably most people have seen many times. So this is showing as a function of sort of different ages of the Earth, sort of the spectrum that you would expect to see. Um, and so the signal that we're really sort of interested in here and pushing to the UV. So if you look below, I don't know, 400, 300 nanometers or something, you can see at different stages of, sort of the Earth's evolution, you get this strong absorption feature due to ozone. And so that's something you can detect with, pretty low resolution, and it's also a really strong signal. And so that gives you, sort of a strong suggestion of uh, life or something like that. So it's a sort of a classic biomarker. Um, so on the left here, I've sort of just copy pasted two blurbs from this XEP Progress in Technology for Exoplanets mission document. So this they update every couple of years. One of them is just saying exactly what I just said. It's this low resolution feature that you can detect at the near UV. And the other is just highlighting that, both Havoc's and Luvoy reports called out, high contrast imaging down to 200 nanometers as sort of a desired capability. But also like this is significantly shorter than any existing mission, either space or ground has ever gone to. And even in the lab, right, no one has gone shorter than, about 550 nanometers. And I think the Roman chronograph also only goes as short as about 540 or so. Someone here should correct me if I'm wrong, but I think that's correct. So this is a science case that people are interested in. But there's been no demonstration at sort of any level of, high contrast imaging capability at these wavelengths. The other perspective from which to think about this is in terms of Hab worlds. So I copied this figure. Oh, was there something in the room?
No.
Oh, okay. Um, from a talk that Lee Feinberg gave at SPIE this summer, and actually I think this has showed up in a bunch of people's talks. So this is sort of the notional instrument suite for the Hab Worlds Observatory, right? So the assumption is that you've got a, sort of a 6-meter class telescope with a bandpass that covers anywhere from the UV to the near IR. And then you've got, at the baseline, a coronagraph, high resolution imager, and then a UV multi-object spectrograph. But the two things I wanted to highlight here is one, even the coronagraph, the notional coronagraph goes as short as 350 nanometers. So that's still pushing toward the UV, maybe right at the edge. And then there's this note about, there's fourth instrument to be defined. And there's sort of interest in defining sort of a standalone high contrast UV instrument. And there were a couple other proceedings that came out of SPIE that were also sort of highlighting the same theme. So there's interest in pushing into the UV. And so our proposal is to sort of do the early technology development to understand what the problems are, and then sort of do an initial demonstration of high contrast imaging at these wavelengths. So this is the proposal itself, is basically these four things. The first is doing the modeling to estimate our contrast limits in the UV. So this is essentially a contrast budget combined with numerical models. And so this is a lot of the stuff that we're already doing for the Space Telescope project, just at UV wavelengths. The second part of this is component level metrology. So this is basically taking the individual elements of the coronagraph system, and then doing dedicated measurements of their different features and their error terms and things like that, and feeding those back into the contrast budget and updating our models with that information. And then the third component is to actually go and then do this on Scoob, right? So the test bed demonstration. In parallel with all of that, we propose to do an exploration of science yield as a function of your achievable contrast as well as UV coverage. So the idea with that is, if we find, based on the modeling efforts, that you can get to, let's say, I don't know, 10 to the minus 9 contrast down to 300 nanometers, then the question we want to answer is, well, what kind of science can you still do with that? Or if it's you can get down to 250 but only at 10 to the minus 8, or maybe there's some threshold or cutoff or something where suddenly it becomes really difficult to get to high contrast. But the idea is to understand what those cutoffs are, and then feed that into sort of predictions for what kind of science you could still do with that. Okay, so then I'm going to go into a little bit more detail through each of these, and describe what it is we're proposing to do, and what we've already done so far, which, spoiler alert, is very little. So the first term, right, so the contrast budget. So I've sort of already said most of this, right? So it's the analytical models and the scaling laws to figure out which terms limit the contrast at the UV. And so on the right here, this is the table I copy pasted out of our proposal, which is highlighting the dominant terms that people tend to consider. And so this is very similar actually to terms we're already including, for both our end-to-end models for Space Telescope project, as well as the contrast budget. But the idea behind this is, I think these terms are pretty well understood at visible wavelengths. But there's a lot less effort that's been done to, push this to shorter wavelengths. And so, you can scale these down, but then the idea is that there might be other terms that dominate, or other, factors that dominate some of these at UV wavelengths. And so right. So the idea is to, to understand these scaling laws as, a function of wavelength, bandpass. And then use those scaling laws to understand which terms will dominate. And then combine that, with end-to-end numerical models, where we, take a Fresnel model and you fold in things like, the sort of the scattering analysis that Chris Mandillo does, and then, other terms like beam walk, or your, errors on your coatings and things like that. And so ultimately the idea here is to produce two sorts of budgets. One is a Scoob budget, right? Specifically aimed at understanding the sort of contrast that we might expect to get on our test bed. So before we actually go and build the thing, we want to make solid predictions. And then that'll let us go and do some sort of validation of our predictions later on. And then the other part of this is to, do a budget that's aimed more at something like Hab Worlds, right? Where we take a notional telescope, and then a notional optical design, which hopefully they will release before long. And then understand what sort of trades we have to make to actually get that budget to close at the 10 to the minus 10 contrast. And so I suspect we'll learn a lot from that, right? Because we'll understand which terms you really have to work hard on, whether it's the quality of the OAPs, or you're controlling your telescope jitter or wavefront stability or things like that. And so then we'll be able to sort of produce some kind of estimate of what we think the big trades will be for Hab Worlds, if you wanted to get to these sort of contrast levels with, a notional design at least. And then I've highlighted at the bottom here just the two milestones in the proposal that are associated with this, right? Just completing the contrast budget. And then as part of that is we want in the first year actually to produce a design of chronograph masks for Scoob. And so that's sort of driven by our understanding of, the contrast performance and the error budget to, to design these such that we would expect to achieve X contrast. And then in later years, we fabricate those, measure them, and then eventually integrate those into the test bed. So we've done a little bit of this modeling so far. This was, again, just lifted directly from the proposal. So this is assuming Scoob optical design with a shaped pupil chronograph designed by Jessica Gershrange. And then on the left here is a 5% bandpass and a 10% bandpass on the right, centered at 250 nanometers. And this is, incorporating a subset of the error terms. So things like realistic errors on our OAPs, DM quantization error, scalping on the DM, polarization aberrations. And so in the one case, we predict that we ought to be able to get to, sort of the 5 times 10 to the minus 9 level in the 5% bandpass, and then sort of the 2 times 10 to the minus 8 in a 10% bandpass. This is, of course, is optimistic, right? So we're not including scattering, we're not including a bunch of other terms. So these numbers should all get worse once we have, higher fidelity models. But it's sort of the initial work that suggests that, yeah, you actually ought to be able to do something in the UV on Scoob. And so it's sort of the start of the contrast budget and then into modeling work. Okay, so the next component of this is the component metrology. And I apologize, I don't have any pictures of things here. And so this is essentially 3 different sorts of measurements. So one is just doing high resolution metrology of things like our reflective surfaces, so the OAPs, flats, and ideally a deformable mirror at different spatial scales. So starting, with the 4D at the interferometer to get sort of low order terms. The Zygo new view over at OpSci, which I believe gets us down to sort of like 200 nanometer lateral resolution. And then finally, what we proposed to do was to use an atomic force microscope, which we do have available to us on campus, to get sort of down to the single nanometer lateral resolution scale. And primarily, this is to understand our surface roughness. And so then by getting these measurements at these scales, we can cross-check our assumptions about how the PSDs evolve at higher spatial frequencies. And then we can feed that into our scattering models. So, the work that Chris is doing with us. So that's one chunk of the direct metrology we want to do. The second thing is take advantage of the BSDF measurement device I believe it's part of Loft. And so this actually does support doing measurements all the way down to sort of the near UV, which I think is down to 200 or 250 nanometers. And so the idea is to do direct sort of near angle scattering measurements so that we can validate, the scattering models from, the step above and then get those direct measurements, which so it validates that, but then also, cross checks. You could potentially feed those directly into your end-to-end model if for whatever reason your models aren't totally reproducing the effects that you're actually observing. And then the last part is we propose to purchase a Mueller matrix microscope that's good to the UV. So there is one at offside, but it only is good to visible wavelengths. So we would have to get another one. And the idea here is to take things like our polarization optics, so the VBC, linear polarizers, quarter wave plates, and then take these measurements of sort of the spatial variations of their polarization properties, sort of at the 1 to 2 micron lateral scale. So we should get pretty fine sampling of, how things like the retardance varies across the surface of these things. Additionally, I'm told you can run these in reflective mode. And so you can also extract, polarization properties of things like our reflective optics. And so it'd be interesting to see if we can, at the sort of the 1 to 2 micron scale, actually measure if there are non-uniformities in our coding that, have some kind of significant effect that wouldn't be captured by polarization model that just falls out of the optical design. So those are sort of the main sorts of things. And then what we would do is take all of these measurements, update our assumptions and models, and then feed that back into the contrast budget. And so then we can update that and then understand, how significantly, the contrast budget changes if we have these sort of as-built numbers from doing this kind of metrology. Okay. So then the third thing, right, is doing the demonstration on Scoob. And I wasn't sure who would be in the room, so I just lifted a bunch of slides from my SPIE proceedings, or rather my SPIE talk this summer. So I was going to just quickly run through the basics of Scoob before diving into what we're proposing to change to do the UV demonstration. So this is Scoob in the TVAC chamber down in 168. This is back in, I guess, May or June. So it is this upper table that's sort of on this dual vibration isolation system. So it's on this -K vibration isolation platform, which is passive and provides just some mechanical isolation. And then again, it's on a second table, which has an additional layer of isolation through these pneumatic bellows. Although I am told that actually might be injecting some really slow, low order sort of drift in our system. So, once we go back to TVAC, we should try not using that first layer of isolation and seeing if that improves our stability. This is the layout. I'm gonna really quickly go through these next slides. We've got our source optics outside of the TVAC, and then they feed into the instrument via fiber. Go through our source optics, which includes a circular polarizer. Got a spatial filter here, which is this microfabricated pinhole that Emery put together. We've got a FISM, our fast steering mirror, relayed to a deformable mirror, which is a 1,000 actuator kilo CDM from Boston Micro Machines with one bad actuator. Our focal plane mask at the moment is a Beamco Charge 6 vector vortex chronograph, nominally spec'd to be good at or spec to a 20% bandpass centered at 630 or 635 nanometers. And then a reflective Leo stop. So this was produced by UMass Lowell. And actually, I think this is the one that's in the system at the moment, which just installed again last week. So that sends the reflected light off to our LOFIS camera. And Keon's been doing a lot of work on getting that running. And then this particular one also has a pinhole, so that the transmitted beam, you get both your nominal science beam as well as an extra leakage term that produces fringes for doing SCC. And then, we've got the sort of the optics at the back end, which are mostly just the circular analyzer and then the science camera. This is actually incorrect. This is not our current science camera. This is what's at the LOFIS. But we switch back and forth between the vacuum packaged one from Neutralino and then the commercial one from ZWO. Okay, so that's the nominal layout of Scoob at the moment. Before we make any modifications, yeah, I think that's true. Before we do any dark hole digging at the UV or any contrast measurements, part of our proposal is to sort of repeat the work that Jaron did, I think in May of this year, where he did these in situ Mueller matrix measurements, except doing this at UV wavelengths, and this is to validate our model of polarization aberrations. I think now we know this is probably going to be very challenging, given the results that Jaron saw, and they weren't consistent with our polarization models. So there might be a bit more work we need to do to troubleshoot this approach. But nominally, this is one of the first things we want to do once we're on Scoob to validate that model. Past that, then the idea is do sort of your classic high contrast imaging experiments in two different configurations. So one is with a shaped pupil chronograph. So that would be using the chronograph mask that's shown on the right here. So this was the design by Jessica. So you'd put this at the fast steering mirror plane, because that is a conjugate pupil. And you'd pull out all your polarization optics. So VPC, of course, has to go, but then also your circular polarizer and analyzer. So that would sort of be the simplest possible coronagraph that you could imagine, right? It's a single pupil plane optic. Um, and so the idea is to get one of these built by it's John Hagopian at I don't remember where he is, but he's in Maryland, and he builds these things with carbon nanotubes to do the sort of the non-transmissive part of this, right? So those have really low scattering. Um, and then for the second configuration would be to throw in a vector vortex chronograph, again, one by fabricated by Beamco, because they apparently have the capability to build these things at UV wavelengths and have done this before. I think the shortest they've done with a vortex chronograph was like 350 nanometers, but they say they have the capability to go shorter than that. So we're gonna have to work with them to sort of spec this. Not notionally, right, we would aim for something that's a pretty narrow bandpass to start, just to make this as easy as possible to fabricate. Um, and then again, we would, install that in the system at the focal plane, and then, include the other polarization optics. There's a couple other modifications we have to make. So our current cameras have very low QE at UV wavelengths. And so we'd either switch to an IMX 487, which is fairly similar specs to our current cameras, just higher QE UV, or we can take our current cameras and apply a fluorescent coating to them. And this is actually, it seems like a pretty well understood process, and we can just send these off to a company and it'll do it for like, I don't know, 1,500 a piece. And they claim it doesn't degrade the optical quality at all. And so, yeah, so when you get UV incident on the fluorescent coating and then fluoresces at visible wavelengths, so you get an effective QE bump on your pixels. And then of course we need to procure a bunch of narrowband and broadband UV sources, and I spec'd a couple of different ones of those when we put together the proposal. These are surprisingly hard to find. um, but the idea is we couple a few different sources into our system, and then be able to test over a range of wavelengths of the UV. And then of course do all this in vacuum. And so then here I'm just going back to the optical design or the nominal layout and just highlighting the sort of the notional changes, right? So you swap out the source, get UV versions of your polarizers. Our spatial filter right now is 4 microns, which I think at, I don't know, 250 ends up being 60 to 70% of a lambda over D. So potentially you start to resolve it. So we might want to switch to a sort of the smallest version of the pinhole that that Emery had fabricated, if necessary. Tip tilt mirrors where we could install our shaped pupil chronograph. The idea is to switch out our Kilo C with an 100% yield one. And right now we're actually talking about procuring a new one in aluminum. So that way we can get rid of our bat actuator, which currently limits our broadband performance and is going to be even worse at the UV. Obviously, focal plane mask is where we put the UV, VVC, and then again, our on the output side, it's just updates to either the camera coding or the camera type, and then our polarizers spec to the UV. And I should say these UV polarizers, the quarter wave plates and linear polarizers, you can just buy off the shelf, and it's similar price to the current ones we have. So those are surprisingly easy to find. Um, and then I think this is my last slide. This is just showing what our work plan is. I'm not going to go through this. But essentially it's contrast budget modeling work in year 1, component metrology in year 2, and then also testbed validation starting in year 2 and then going into year 3. And notionally this starts in October. So we're actually meeting next week with someone at NASA to basically do the kickoff meeting of this. So this will be underway really soon. So yeah, I guess the start of year 1 is, a week or 2 away. So the first thing we have to do is put together a white paper. And then once the white paper is out and then approved by NASA, then the official start of work begins. So really, maybe it's more like sort of the December timeframe where this work actually kicks off. That's all I have. Are there any questions?
Sorry, we were muted. I'll ask a question, Kyle. Uh, so I guess one of the other possibilities to do high contrast UV is to use a star shade. And so I'm wondering, like, what are some of the advantages to using, like, doing coronagraphy rather than using a star shade?
I suspect it's the same advantages as doing it at visible wavelengths, which is star shades are really expensive, and you can't test them prior to building the full thing. Um, I mean, in some ways, like I don't know. Has anyone done the trade of like what sort of um fabrication tolerances you have and everything for a star shade at UV? Because if it's similar to the visible, then in some ways it would be more compelling at the UV. Because I suspect what we're going to find is it's really hard to get a high performing coronagraph at UV wavelengths. But if a star shade scales better to the UV, then my worries will find you can never do 10 to the minus 10 at 200 nanometers. But maybe you'd find with a star shade you could do 10 to the minus 10 contrast.
Yeah, I guess I'm wondering, like, maybe it's also kind of like a scope and cost thing as well, because I imagine it's a lot more complicated to do all of the like the integration, the testing, the Starshade case, and I mean
Yeah.
it seems like it's a lot more money, but maybe that's not. I don't know. Maybe it's just because we haven't really done Starshades before.
Yeah, I mean that's my understanding, right? Is star shades haven't been done because you have to commit to 100%. Like you can't do
Yeah,
you can't do like a little cheap tech demo to figure out if it works. You have to commit to the whole thing. Um,
yeah.
and so then if it fails, it's there's yeah, that's it, right? But I think if what comes out of this is you just can't get to the contrast you want with a reasonable instrument design, then maybe one of the conclusions will be you just have to do a star shade at UV, right? Because the advantage, right, is the star shade is upstream of all of your optics. So the only thing you have to really fabricate really well is your star shade, and then you can have like a really you can have optics with a lot of surface error and things like that, I think, downstream. At least more, right? You still have scattering and things like that, but it's a lot less, right? Because you've already rejected most of your starlight. Um, so it might be more compelling at the UV to do a star shade.
I want to say there's a big difference in expected yield, which is one of the major strikes against it because you can't observe nearly as many targets on it.
Yeah, because you always
Yeah.
because you
Yeah.
have to move the star shade into
Yeah.
place. Yeah.
Yeah, that's true. But again, it's the same as at the visible, right? It's
Yeah.
I have a question, on the science part. So you mentioned that the ozone could be a biosignature. Did you thinking about any other possible in UV weapons other than ozone action?
I think there are. I am less familiar with all the science cases, so I'm not the best person for that. So Justin, I don't know if you want to take a stab at that.
Sure. Yeah. I mean, like, for the specific science case of like terrestrial planets, I mean the ozone feature is just really compelling because it's really strong and it's really deep. But like you could imagine other science cases that are not terrestrial exoplanets that going into the UV would be useful for. So for example, like um, if you look at really young planets, for example, really young and maybe they're still forming, you can actually get emission in the UV from just the planet secreting material. So it's like there's like an excess of UV emission, like shorter than about like 350 nanometers or so. Um, and like I think people have kind of done this with HST, or maybe I think people have tried to look for it in HST, but I don't know if, I don't think we've had a lot of detections of that. But I mean, maybe it's just that we haven't reached, we haven't been able to reach the sensitivity with HST in order to see those kinds of signatures. So you can imagine like maybe this is what we would need in order to be able to detect that. Hopefully I have to cut it out. Thanks, Kyle.
Thanks.
Thank you.
Thank you everyone for coming, guys. We have the next class, the same time next Tuesday.